Well, I thought I was going to be done with graphing, but this one I couldn't resist it when I saw it because it has a lot of things going on it that I think will be useful for my calculus students. In particular, there's a lot of things. I have a rational exponent, which I haven't done much outside of the square root function, so this should be a very useful example. So, with that in mind, let's start with the domain. You can plug anything in for x here because when you square it, it's still a real number, and then we take the cubed root, it's still a real number. So you don't have any problems here with it being defined versus not defined. Now, if that was an even root, like it was 2/4 or 1/4, then you would only be allowed to have non-negative values for x. Over here, this part's a polynomial, and that's defined for all real numbers. So our domain is -infinity to infinity. The range, get that at the end. Let's find out where the intercepts are. And I'll start with the X-intercepts. So we'll set this thing equal to 0. And of course, to solve an equation like this, you set each factor equal to 0. If x to the 2/3 is equal to 0, all I have to do is take both sides to the 3/2 power. 0 to the 3/2 is still 0. And then this piece, I don't know if a factor. I mean, there's a lot going on, a lot with the numbers. I'm going to just go straight to the quadratic formula because I really don't want to try to. I can do the quadratic formula faster than I can probably factor it anyway. So x equals 8 plus and minus the square root of -8 squared plus 4 times 9 times -16. All of that is over 2 times 9. That equals 8 plus and minus the square root. So I have 64 plus 576. All over 18. 64 plus 576 is 640. And I can take a 64 from 640, and when I pull it out of the radical, it will become 8. Not a lot of simplifying, but I can cancel out 2 in the numerator and 2 in the denominator to get 4 plus and minus 4 radical 10 over 9. So let's write these out. The x-intercepts are 0, 0. You plug in 0 for x, you're going to get 0 for y. So that's both an x and a y-intercept. And then we have 4 plus and minus 4 radical 10 over 9, 0. So this one right here takes care of the y-intercept right off the bat. I don't have to worry about it. Now, let me go back and rewrite the function. I think that was 16. I'll check it just to be sure. Now, to take the derivative, you probably might be thinking of using the product rule because this x to the 2/3 is multiplied to the second factor. I'm not going to do that. What I'm going to do is multiply the x to the 2/3 through. I'll show you why. Because 9x squared can be thought of as 6/3. 8x can be thought of as 3/3. And a negative 16, nothing special there. That way when I multiply through and add exponents, here's the thing I will get. I'll get 9x to the 8/3 minus minus 8x to the 5/3 minus 16x to the 2/3. That way you can just use the power rule throughout this whole thing instead of worrying about a product rule and then trying to make powers work when you add everything up together. So I'm going to use this version of it for my derivative. So I'll get 72 over 3 x. Now you got to subtract 1. You got to subtract 3 over 3 from that 8/3 and get 5/3. Then I have minus 8, but I multiply by the 5/3, so that'll give me 40 over 3 minus 40 over 3 x to the 2/3. And then I'll multiply 16 by the 2/3 to get minus 32 over 3 x to the negative 1/3. Now, it may seem weird, but I'm going to refactor now. And whenever you factor out x's, always try to pick the one with the lowest power as the one that you factor out. So what I'm going to do is factor out this 1/3 from everything. And then, I don't know if you noticed, but 8 goes into 72, 40, and 32. So I'm going to factor out an 8, and then I'm going to factor out an x to the negative 1/3. So I'm going to factor out the 8/3, like I said, x to the negative 1/3. And what that leaves, when I take 8/3 here, that will leave me with a 9x to the 6/3. And when I take a negative 1/3 out of this part, I will get, well, the 8/3, when I take that out, that will leave me with minus 5 x to the 3/3. And when I take an 8/3 out of here, that'll be leave me with a 4, just a 4, minus 4. And then I can simplify these exponents so that I have a quadratic. So that's times 9x squared minus 5x minus 4. Now, one critical number that you get right off the bat is x equals 0. The derivative is not defined when x equals 0 because of this negative exponent. So let's keep that in mind. The other critical numbers I'm going to get by setting this part equal to 0. Once again, I'm going straight to the quadratic. So I get 5 plus and minus the square root of 25 plus 144. This kind of tells me that somebody was working to make the problem at least work out somewhat, because 25 plus 144 is 169, which just happens to be a perfect square. We have 5 plus and minus the square root of 169 all over 18. That's 5 plus and minus 13 over 18. So what are those numbers? We get 5 plus 13 will give me 18 over 18, so 1. And then 5 minus 13 will give me negative 8 over 18, or negative 4 over 9. So those are two critical numbers. Don't forget that we had x equals to 0 because the derivative is undefined at 0. So my critical numbers for f prime are 0, 1, negative 4 ninths. All right, so I have to pick numbers in between these things for it to work. Now, I think I'm going to stick with this format to tell me where things are positive and negative. So let's go ahead and go through that process. Since, also, I want to point out one other thing. I'm taking things to the 1/3 power here. So it'd be nice if you could pick numbers that had good cubed roots while you were doing it. For example, a good cubed root to the left of negative 4 ninths would be negative 8. Its cubed root is negative 2. Let's take a look at then what we'd have for x equals negative 8. I want you to think about it. When x equals negative 8, this part is negative 2. So out front is a negative number. But in here, when you take negative 8 and square it, you'll get a 64 times 9, which will be 540, 576 plus 40 minus 4. What I'm getting at is this piece here is positive, but this piece here is negative. So when you throw in negative 8, you get decreasing. So what kind of trick can I play in here to where I get a number that's not so horribly bad to use? And in here what I'd pick is negative 1/8. So let's see what happens when I throw that in. If I throw in negative 1/8, this piece right here is going to be a negative 2. I think I might have misspoke last time. When I plugged in negative 8, this part right here would be negative 1/2 because of the negative exponent. Now when I plug in negative 1/8, this piece right here will be negative 2, negative. And then what happens inside of here? I get 9 over 64 minus 5 over 8. Plus 5 over 8 minus 4. I can tell that the minus 4, its negativity is much greater than this part's positive. You can check it out for yourself. But that tells me that I have a negative times a negative, which gives me a positive. So that I am then increasing. So this value of x here will give us a local min. Now let's see what happens between 0 and 1, and I can play the same game. I'm going to, inside of here, I'm going to pick positive 1/8. See what happens. If I plug in positive 1/8, then this becomes a positive 2. But then, when I put 1/8 in here, I'll get 9 over 64 minus 5 over 8, which is already negative, minus 4. So, I have a positive part times a negative part will end up being negative. So 0, at 0 we have ourselves a local max. You might wonder why it's a local max when the derivative is not defined at 0. Well, the original function is defined at 0, so there's actually the point 0, 0 is actually on the graph. So what it's doing before and after 0 forces it to be a local maximum, but its derivative doesn't exist there. All right, now let's pick something after 1, and I'll play the same game as before. I'll put an 8 out there because it has a good cubed root. Let's see, if I plug in 8, I'll get 1/2, so it's positive out here. And then in here, when I plug in the 8, I'll get 576 minus 40. this will be a positive times a positive, positive. So at 1 we have a local min. Let's determine what these values are. You got to plug these into the original function. So I'll start with f of x. The version I think might be the easiest for the original f of x was x to the 2/3 times 9x squared minus 8x minus 16. Let me plug in -4/9. So I'll have 4/9, -4/9 to the 2/3 times 9 times -4/9 squared minus 8 times -4/9 minus 16. Now this part, what I'm going to do is apply to the second power first. So I'm going to get 16 over 81 to the 1/3 power. Notice how that changed to positive because of the square. And then I'll have 9 times 16 over 81 plus 32 over 9 minus 16. Now what I think I'll do next is I'm going to break this piece up into a part that you can take a cube root of and a part that you can't. So I'm going to write this as 8 times 2 divided by 27 times 3. And that's to the 1/3 power. Inside of here I'll cancel a 9 into the 81. And I'll get 16 over 9 plus 32 over 9 minus 16. The cube root of 8 is 2, and the cube root of 27 is 3, so I'll get 2/3, and then the 2/3 that's inside of here I can simply write as the cube root of 2/3. And then I'll add these two together to give me 48 over 9. Now I can rewrite this as 144 over 9. So that gives me, it's going to end up being a negative number. I'm going to get negative 94 over 9. So I'll go 2/3 times the cube root of 2/3 times, let me see, 104 take away 8, 96. Okay, negative 96 over 9. Well, that's nice. You got at least a little bit of canceling goes on here. Say a 3 goes into both 9 and 96. If I cancel out a 3 here, and then a 3 here, I'll have a 32. So I'll rewrite the final answer then is negative 64 over 9 times the cube root of 2/3. This was a local min, I believe, wasn't it? Yes, a local min. So, for what other one do we have? 0, well that's easy, I've already plugged that one in. F of 0 equals 0, that's a local max, 0, 0 is a local max. And then I have another local min at 1. F of 1 equals 1 to the 2/3 times 9 times 1 squared minus 8 times 1 minus 16. That equals negative 15. So let's see what we have then. Local mins. Negative 4/9, comma, what was that crazy number again? Negative 64 over 9. times the cubed root of 2/3. And then we had 1 negative 15. Then a local max that was 0, 0. Decreasing and increasing. So let's see, where is it decreasing on? We're decreasing from negative infinity to negative 4/9. And I know there's more, so there's union something here. Union 0 to 1. And increasing on, well, what would be in between and around, so negative 4/9 to 0. Union 1 to infinity. So I think that's about all we can do for the first derivative. Now let's move on to the second derivative. I want to copy my first derivative down again. There's f of x. F prime is what I need. F prime is similar. We have 8/3 x to the, well, make it easier on myself then. Actually, when it comes to taking a derivative, I think I'd rather have this version. And then I'll go and strip out what you might call the irrational stuff, if you will, later on, like I do in the rest of these problems. So let's throw it in here. And while I am here, I'm going to simplify a little bit. 72 over 3, that's 24. X to the 5/3 minus 40/3 x to the 2/3 minus 32/3 x to the negative 1/3. Now let me go and take the second derivative. So we'll bring down 5 times 24 will be 120, but then I'll divide by 3. Well, that's nice. That'll be 40. 40x to the 2/3. Make sure you subtract 1 off. 5/3 minus 1 is 2/3. And then I'm going to get 80 over 9, negative 80 over 9, x to the negative 1/3. And then finally, I'm going to get plus 32 over 9, x to the negative 4/3. Now, it's hard for me to determine zeros and all that kind of stuff when it's in this form. So like I did before, I'm going to factor out the lowest possible x power of x, which is x to the negative 4/3. Now, while I'm here, notice that 8 goes into all of these numerators, and I can factor out a 1/9. So here's what I'm going to get. I'm going to take an 8 out of everything up here, and then I'm going to take out a 9. Now what happens then is when I take the 8 from 40, I'll be left with a 5, but then when I take the 1/9 from it, 9 times 5 will be 45. Remember how this goes. 2/3 plus 4/3 will be to the 6/3. Then I'll have minus 10 x to the 3/3, and then finally plus 4. And once again, this provides us with a critical number of 0 because it's not defined there. To get the zeros of this, I'll go with the quadratic formula again. Remember, this 6/3 is squared, 3/3 is to the 1 power. I'm going to go with the quadratic formula. So I'm going to take negative 10. That'll be 10 plus and minus the square root of negative 10 squared minus 4 times A was 45, C was 4, all over 2 times 45. That equals 10 plus and minus 100 minus 720 all over 90, which I can stop right there. Since I'm going to get a negative number inside of this radical, these numbers are not real numbers. So what that means is I don't get critical numbers based on the zeros in this part. In fact, if you take any, let me explain this a little bit further. Since it doesn't have any real zeros, that means that this parabola is either completely above the x-axis or completely below the x-axis. If it's above the x-axis, it is opening up, which we know, since it starts with a positive leading coefficient, that this particular parabola does open up. That means that this quantity is always a positive number. The only critical number, therefore, is x equal to 0. So the only critical number for f prime prime is 0. So I'll go ahead and do my number line. Well, this is going to be super easy, because if I plug in a negative number, once I take that negative number and take it to the fourth power or the negative fourth power, it becomes positive. We already know this is always positive. Same situation if I plug in a positive number. Positive times a positive will be positive. So it's concave up, concave up. So we are concave up on negative infinity to 0, union 0 to infinity. The reason why I don't include 0 is because even though 0 is in the domain, the second derivative is not defined there. So there's no concavity happening at 0. However, it's concave up everywhere else. We have no points of inflection. So I think I'm ready for a rough sketch of a graph. Let me go ahead, and then of course we'll check it always with the computer's graph. Let's see the numbers that were important for us. Let me first get the zeros, and I'll plot them on there. So the intercepts are 0, 0, and 4 plus and minus 4 radical 10 over 9, comma 0. 0, 0 is easy enough. Since I want things to be fairly, positioned relative to each other correctly, I'm going to sneak a peek at some of these fraction, or these numbers that we've been dealing with. So for instance, the 4 plus 4 times the square root of 10, enter. And if I divide by 9, I'm about 1.85. The reason I mention is because I know I've got something going on at 1. A local something is going on at 1. So this is almost double that. Let me put a dot there instead, because we're actually crossing at this spot. 4 plus 4 radical 10 over 9. And that 10 looks like a 16. I was able to take it out of there. Thank you. Now let me do the same for the 4 minus 4 radical 10. So I'll do 4 minus 4 radical 10. Enter. And now I'll divide by 9. That's negative 0.96. That's about -1. So I'm going to put it in about the same general location, but on the other side. So this one right here was 4 minus 4 radical 10 over 9. All right, let's see what else we had going on there. So the graph has to go through these things. Now I've noticed then we're concave up and we are decreasing until we get to, I remember, -4/9. I'll put it right about here. So we're decreasing until we got to -4/9. And what that was that really weird number. Let me see what it was. This one right here. Let me get sort of a vibe on how big that number is by going to the calculator. So the first thing I'll do is I'll do 64 divided by 9. I'll enter that. And then what I'll do, the way I do it is I do break it up into pieces, times. Now what I can do now is take 2/3 to the, oh, I don't think you even need that. Let me delete that character. 1/3. A little more than 6. And I've got 1 -15 also, so let me throw those in there. So if 1 has a -15, let me throw that here. And then the other one was about -6. That was at -4. So if this is 15, let me see how many marks. 1, 2, 3, 4, 5. So each mark is about 3. So I'll throw it a little more than -6. And this is -64 over 9 times the cubed root of 2/3. And that's also a local minimum. So we're concave up from -infinity to 0, so it's got to do something like this. And come over here. And the reason why there's no change in concavity is because then it's got to go from that point and make it all the way down to here in a concave up manner. So I think I got it there, and then I got to go over to that point. So there is my completed rough sketch. What I want to do next is have the computer graph it and just see how right I am. Well, here's the graph from the computer. Let's see how it compares. It certainly looks about the same. Sort of like a lopsided McDonald's symbol upside down. Let's see. Let's check some of the numbers here and just see if it all jives. First, the easiest one, 1, -15. Is that on the graph? I've sort of stretched it sideways so it's easier to see. 1. Yeah, these go by 2, so 1 -15 is definitely there. Okay, now remember I said the 1 was like 1.8 something, so that certainly, since this is 1.2468, that certainly makes sense that would probably jive with 4 plus 4 radical 10 over 9. The 0, 0 is pretty evident. Nothing needs to be said there. Now the other one, I think that was about -0.96, a little bit. So this is -1, so it is a little bit greater than -1. So there is 4 minus 4 radical 10 over 9. And then what about the one that was at -4/9? Could that be? Well, if these go by 0.2s, there's 0.2, there's 0.4, and 4/9 is 0.444. Well, 4s repeat forever. So that certainly seems to be the case there. And the other number was a little like -6.2, so all of these things seem to jive with all the information I got. So this last point here, I'll put an arrow to it. That was -4/9, comma, -64/9 times the cubed root of 2/3. So, while I'm able to use my calculator to help me out, I'm still able to get exact answers here. So that's all for this particular problem. I think it's finished.